Okay then, what is the language of standard model? How does it communicate to us what the standard model has to say about the overall makeup of the cosmos? So we'll be going through the language of standard model. We can see that a simple picture emerges out. There is a Higgs field permeating throughout the cosmos. It is a matter field, a very subtle matter field, an energy matter field which permeates the whole cosmos through and through, everywhere. And the same Higgs field gives mass to different types of particles as the particles move through the Higgs field. Then we have got 24 particles. The particles which are found free, like leptons, and the particles which are found bound in protons, neutrons, etc., that is quarks. Now if we see, there are leptons, there is an electron, there is a tau, there is a muon, positron. Positron is an antiparticle of electron. So in all there are 3 leptons, electron, tau, muon. Then we have got their antiparticles, that is anti-tau, anti-muon. Then we have got their neutrinos, the electron neutrino, tau neutrino, muon neutrino, and their antiparticles. In all they make the 12 particles or 12 leptons. On the right side we can find the quarks. There are in all 12 quarks: top quark, up quark, charm, strange, down, and bottom quark. And there are 6 anti-quarks: anti-top quark, anti-up quark, and etc. So in all we get 24 particles. Then we have got the 4 forces at the center of the particles through which particles interact, through which these particles communicate, or which help particles to bind to each other and give the makeup to the cosmos. These are called bosons. There are W and Z bosons, which are for weak force, and they help leptons to communicate with each other, like neutrinos. Then there are photons, which give the electromagnetic force, binding the electrons, positrons, etc. together. Then there is a gravitation force, which is a long range force and a very weak force. On the right side, we can find only one boson, that is gluon, which binds the quarks together. But overall nature of the Higgs field, which is the matter energy field and permeates the whole cosmos, is not fully well understood. And so with all the bosons, boson fields and the forces through which they interact. Much more needs to be done to understand the right nature of these forces which help to bring our cosmos about. Now, all the particles, whether they are baryons like protons, neutrons, or fermions like leptons, quarks, or bosons like W and Z bosons, photons, gluons, they all get birth in the detection system. As you can see, the center of the tracker is the site of origin. And these particles travel through the different layers of detection system. Since the particles are subtle and have a very high energy, they pass through different layers of detection system and get detected by different methods utilized by the specific model of the particle physics or high energy physics. We see that in the tracker there is a forward tracker and a backward tracker. In the middle of the belt of detection system, like Atlas, AMS or LHC Beauty, the tracker keeps the track of all the particles which pass through the tracker barrel. They form the track of every particle, every activity. Then, next layer is electromagnetic calorimeter barrel. The electromagnetic calorimeter barrel traps and registers and detects the charged particles like electrons, positrons, and photons. Then we have got another layer of detection system, hadron calorimeter or HCal barrel. The hadron calorimeter registers the hadrons like neutrons, protons, and the quarks, diquarks, tetraquarks. There are tetraquarks, pentaquarks. They are all registered in HCal barrel. Next we have the muon chamber. There are neutrinos which can escape all the detection layers. There are neutrinos which escape even pass through all the layers of Earth through to the other side of the Earth. They are the highest energy particles which can pass through all the detection layers, and for them there is another method of detection, that is muon chamber. All the neutrinos and antineutrinos get detected in the muon chamber at different levels. You can see in the detection system Then we have got the end caps, the hadron calorimeter end caps. We have got the plugs. We have got the end caps for electromagnetic calorimeter barrel and muon end cap. So that's the detection system where all types of particles get detected after their birth, and they register themselves in different detection systems.
This is the Phaser detector. It's located in the LHC tunnel 500 meters away from the ATLAS experiment. Phaser looks at particles produced in the proton-proton collisions inside ATLAS. Specifically, it focuses on low-mass particles that are produced along the direction of the proton beams. As these particles decay, they produce, among other things, very high-energy neutrinos. These neutrinos will continue along a straight line, unaffected by the magnetic fields guiding the proton beams around the LHC ring, and by the rock between ATLAS and Phaser. The neutrinos can then be detected by Phaser when they interact within a 1.1 ton block of tungsten positioned in front of the detector. For a muon neutrino, such an interaction would produce, among other particles, a high-energy muon that can be detected in the tracking system of Phaser.
I think the time resolution of this chip is one of the main things that makes it special. The TDC-Pix measures time intervals, and it does so very precisely. So time interval measurement sounds exotic, but it's not.
Principles is to measure the transition time of particles from one layer to another.
Most people
you can see a chip in place which records the time of transition of particles from one layer to another.
The time that each runner takes to run from the start signal, which is the start gun, to the point where they cross the finish line.
With 64 particles, 66 more than 66 particles in place, more than 66 particles have been found. Now, how do you name and classify? What is the basis of naming and classifying the particles? What we do is that we track the spinning of the particle, the polarization of the spinning of the particle. We see the charge of the particle. We classify and name particles on the basis of charge. Second, then we see if diagonal pulse, we see the mass. What is the total mass of the particle? What is the total energy it registers? What is the total energy of the particle recorded in the detection system? Or some particles decay very fast into other types of particles. They leave their traces. We record the time of decay. How much time does the particle take to decay? So these are the methods employed by the detection system to name and classify the particles.